Hello, my name is Barbara Bruno. I am a postdoc researcher at the Chile lab in EPFL in Switzerland, in Lausanne. My personal background is my current research is in robotics and specifically in human robot interaction, which is where my background is. And what I am doing here specifically is to use robots and see how we can use robots to support education and special education. So the Chile lab, in fact, is led by Professor Pierre de Lambourg, who is one of the most famous researchers worldwide in learning and collaborative learning specifically. So the way we use QTrobot is exactly to these purposes, to see how robots and social robots especially can support children in understanding concepts. And the specific tasks that we are dealing with are either concepts which are not traditionally thought in other ways. And so we want to investigate whether a robot can be a good mean to convey these new concepts to children. And another area of research is to explore whether robots can be used to support children that have specific difficulties in overcoming the difficulties and be on par with their peers. So concretely, what we do is on one side, we have two funded projects that we are working on where we use QTrobot. One is Animatas. It's a training network funded by the European Union. And in there, we use QTrobot to try and convey computational thinking skills to children. And specifically, we're looking at graph-based reasoning. On the other side, with another project, which is called IRECHEC, and it's jointly funded by the French National Research Foundation and the Swiss Science Foundation, we are investigating whether we can use QTrobot and its social capabilities to support children who have difficulties in handwriting to improve their handwriting skills. So to give you a brief overview of these research lines, on the first line, so QTrobot for computational thinking skills, that is actually, again, further subdivided into two lines. So on one line, the researcher primarily involved in this is a PhD student from the lab, Javeria Nasir, and the goal there is to see how can the robot support two children who are interacting together, playing together a collaborative activity. How can the robot support them in the activity to be more efficient, to lead them to be what she calls productively engaged with the activity? So the tricky part here is that it can happen very often that when you have a robot involved in a learning activity, the robot sort of captures all the attention, and the children end up being very much engaged with the robot, but not learning because they're not paying attention to the activity. So what we are investigating with Javeria in this specific project is how can the robot take the attention of the children and direct it in a way which is conducive to learning. So how can the robot mediate between them and the activity to support them into learning? The second line that we have around this robots for computational thinking is led by, it's primarily led by a PhD student in the lab, Utku Norman. And what he investigates is instead whether giving to a robot capabilities of mutual modeling is important and beneficial for learning. What we mean here is that we no longer have two children collaborating with each other, but we have one child collaborating with a robot. And the idea is, can the robot, what if we give to the robot the ability to keep in its mind the way the human is seeing the activity? In this way, the idea is that the robot would be able to see if the child has a misconception about the activity, and therefore the robot can then act to correct it, and therefore support the learning of the child in a very natural and collaborative way. On the specific case of graph-based reasoning, for example, a typical misconception is that children consider it as a problem of graph traversal. So I go from this point to that point, but sometimes the problem is not about traversing a graph, but it's about building an optimal network. And this type of misconceptions can only be solved if let's say if they are surfaced. So the goal here is for the robot to keep this representation of the way the child is seeing the activity, the way the child is also viewing the robot choices, and build on that, use that in the collaboration with the child to try and, again, as always, lead the child to better learning, which is always in the end the purpose of all the activities we do. Now, these two are for computational thinking. The third line is instead about using a social robot to support children in handwriting. The motivation for this is that handwriting is one of the basic skills that are needed for children, and especially in the early years of primary school, children show their competence in many fields, in math, in science, in history, in geography, through handwriting. So having difficulties in handwriting has a very big, deep impact on the self-esteem of a child and can lead to very bad consequences later on, with long-term consequences in their life. So the idea here, we are building over a previous project from the lab, which is called Co-Writer. And the idea is to use the interaction between the robot and the child in a way so that the child with handwriting difficulties is the one that is teaching the robot how to write. And therefore, there is no feeling of, I have to do another, yet another exercise. Now it's even a robot that is telling me how to write. This is completely reversing the perspective. We are adopting what is called the learning by teaching paradigm. And our using here of the robot is to act as let's say the student of a child, the learner, and also to mediate between the child and a platform of let's say learning exercises to promote handwriting in a way, so with the goal of keeping the child engaged into learning exercises in a way that is positive, and therefore that will help the child practice more. From a research perspective, in the line with Javeria, so the line where we investigate productive engagement, the first thing to do was actually to see whether productive engagement exists. And the way we tested that was to have by having two children that are cooperating on this graph-based activity, which is actually realized as a game, a collaborative game in which the children have to jointly build a railway network connecting the gold mines around Switzerland. And in that first case, we tested it with approximately 100 children coming from two schools in Switzerland. And in that scenario, QTrobot was the CEO of a gold mining company, asking the children for help in building the railway network. It was important for us that in that case, the robot was present, and that robot was doing absolutely nothing to help them in their task, in the activity. And we examined then later on, building on the visual information, audio information, the children's interaction with the activity itself, pre and post test. We assessed their learning gain, and we tried to assess to find ways to connect the way they behave during the activity and the learning. And what we found were some nice insights on indicators for learning. And interestingly, one thing that we found is that the way they speak with each other, and actually even elements like overlap, so being very much involved in the activity is related to learning. So it seems that the more the children talk to each other, and actually the more they learn. So building on these findings, we created a new version of the system in which the robot, QT, is no longer a passive element, basically, But this time it tries, it is equipped with this notion of what is good for learning, what behaviors are seems to be working, what behaviors seems to be not working, and the robot tries to give suggestions on how to act. So at the moment, we just tested it in an online experiment in June that involved 20 participants. Um, and what the robot was doing in that case was from time to time to suggest, why don't you discuss about the edges that the railways and segments that you're adding, because maybe we are putting more than necessary. Or at another time, it would give another suggestion with the idea of prompting them to reflect and to speak with each other in this way, which we found to be leading to learning. One interesting element was at the end, we were asking the children about their impression of the robot. We used the Godspeed questionnaire, and we used questionnaires, and there was also an open interview moment. And I think that my favorite answer there was when one child, that when asked, what did you think of the robot and the robot suggestion, he said, our QTrobot was exactly like my parents, always telling me to do things that I was already doing. And that was a very nice image for a robot, and also an unexpected assessment of parents. The idea along this line is to have another experiment that will hopefully be running soon, in which the robot is in real time assessing, based on the behaviors of the children, which type of learner they seem to be. So are they people who tend to explore broadly and then converge to the solution, or are they people who seem to act locally and reflect on each segment, whether it's the right or wrong, and slowly build up the solution. So based on their behavior, the robot will try to characterize which type of learner they are. And based on the type of learner they are, the robot will try to provide personalized suggestions to them. Again, as always, in the hope of leading them to better learning of the problem, of the concept. It will also be interesting to see on par how is the children perception of the robot changing with the increase in robot capabilities. Because one thing that surprised us is that with respect to the first robot, the one that was doing absolutely nothing to help them, even the children who failed in the activity said that the robot was wonderful, very intelligent, and they didn't need any more help from the robot. So while conversely, the second version that was already trying to give some help, then more children said that, yeah, the robot could have been more helpful. So we have to check it, but it will be interesting to see whether this trend is confirmed. So the more a robot is helpful, and then actually the more people want even more support from it. On the line with Utku, Norman, the goal there is to build this mutual modeling system. So how can we endow a robot with mutual modeling capabilities? That one we do through partially observable Markov decision processes, actually. And the other element, which is very important, is, okay, and once the robot knows what is going on in the child mind, how can the robot act on it? So we tested a version of the activity, again, in June with 10, I think, participants, in which the robot was giving suggestions to the child, and the child could agree or disagree with the suggestion. And what was very interesting in that case is that that time the robot was following the wrong strategy. So the suggestion of the robots most of the time were wrong. And it's interesting to see that even in those cases, when the robot was given wrong suggestions, first of all, the children were not fooled by that. They had no hesitation in saying to the robot, you're very wrong, I reject your suggestion, you have no clue what you're suggesting. And their solution, the ones that they found when collaborating with the robot, even though the robot was wrong, those solutions were the best. So it seems that the robot, even this way, was effective in making them reflect on the correctness of their own solutions, the ones, the suggestion from the robot, and improve their understanding of the whole problem. Again, the idea will be in the following to design a new version of the system where the suggestions of the robot are better tailored to the robot's understanding of what is going on in the child's mind. In the last experiment, so in ERECheck, where I am working together with my postdoc colleague Daniel Tosadore and a PhD student Chenyang Wang, the goal in there is to make the robot able to interact autonomously with the child and to sustain the whole interaction. Because the problem that we have is that therapy for helping children exercise handwriting is nowadays very costly. And it requires experts or support teachers, and schools don't have the resources for giving a one-on-one time with a support teachers to all the children which are in need of handwriting support. Just to tell you, approximately one child, every 4 has handwriting difficulties. So the goal is to have QTrobot able to autonomously manage the interaction, and when the robot is alone. But at the same time, whenever there is a support teacher, or whenever we are in a special education context and there is an expert there, then the robot should immediately let the human expert take over and resort to a supporting role. So what we are investigating there is how can we design a system where the robot autonomy can be modulated and increased or decreased at need, and also where we can use reinforcement learning mechanisms, for example, to have the robot that learns from the human experts how to better manage those sessions. In parallel, another thing that we are exploring in there and that we just started is the relation, whether there is any connection between the child's posture while handwriting and the handwriting quality. And in this case, it would again be very nice if there is such a correlation, then we could be using the robot to monitor this fact as well through its own camera and possibly also an external camera, and use this posture information, for example, to detect losses in attention or the increase in fatigue, and propose breaks or some physical exercises to break the handwriting, resort to a good mood and a better posture, and then resume writing. So with the idea, as always, to help the child in overcoming the difficulties with handwriting, also from this motivational level. The way we use QTrobot, as you saw as you heard in the descriptions, is really it's basically AI. So it's from a computer scientist perspective, in a sense. So what we are really doing is we're not so much interested in the physical capabilities of the robot, but we are interested in what goes on in the robot mind that drives the social interaction with the children. It can be on giving suggestions for what to do on the activity, or finding motivation for to motivate a child towards a handwriting. So the one thing that I think it's the best feature of QTrobot, and also the one that I like best, is that it never breaks. It's robust. It's a wonderful robot, because many times it happens in research when you are dealing with social robots that they break, and your research is affected by the fact that a hardware failure prevented the experiment from going as it should have done, and therefore it prevented your work to really appear in the experience of the user. From a personal level, since I am the one responsible for making sure that my PhD student can do the research, the fact that this robot never breaks is wonderful, because it means that I don't have to care about that, and we can really test out our research and their research in the experiments. This is wonderful. Another thing that we see very, very important is that, for example, in the case of handwriting in the ERECheck project, we are really using many of the sensor of the capabilities of the robot. We use the Wi-Fi connectivity so that it can directly take information from the tablet where we have this joint activity running. We use the camera for extracting posture-related information, for example, to compute the distance between the hand of the child and the head. We make it speak. We make it show different expressions on the face. We use the face recognition system, the skeleton tracking, and the fact that everything is built in and there is quite a powerful system to support it makes it a very rich platform for exactly this type of studies. It's rich and it's robust, and I think that I couldn't ask for anything better. However, if I can ask for something better, in the handwriting case, especially, it would be very nice if the robot was able to actually write, rather than mimicking, for example, writing on a tablet. So I know things come at a cost, and there are always trade-offs. But a few more degrees of freedom would in the arms, and they would be very nice, so that they would allow us to have this richer and more realistic interaction with the children. At the same time, since we are many people that are working with the robot, and also we have students that join us for a semester project, for example, so the robot becomes a very rare and scarce resource, a very precious resource in the lab. Having a simulator that allows different people to quickly test their things from a social perspective, or even an interaction, using the simulator prior to testing with the robot would be a very nice element that supports us in our research.